Dear students, in this seventh part of video dealing with permutations, I'll be introducing two important concepts, namely orbits of a permutation, and there are special kinds of permutations called cycles. So first we'll deal with what is meant by orbit of a permutation. Means given a permutation, what we mean by its orbits. And after that, we'll have some permutations in Sn which are named as cycles. So for learning cycles, we require the definition of orbits for defining cycles. So orbits are to be carefully understood first. For learning orbits, you have to recall the definition of equivalence relation. A relation on a set A is called equivalence relation if it is reflexive, symmetric and transitive. So if you have an equivalence relation, it cuts your set A into equivalence classes. So these equivalence classes, we'll see that they are the orbits of a permutation. So let's go to the definition. Orbit of a permutation. Let A be a given set and let sigma belongs to SA. That means sigma is a permutation on A. We define an equivalence relation tilde on A as follows. A is related to B if there exists an integer n such that B is equal to sigma raised to n of A. Sigma raised to n of A means sigma composition n times sigma is operated, then you will be getting B. So that n may be 0, 1, 2, 3, etc. minus 1. If it is minus 1, it is sigma raised to minus 1. That means inverse of a permutation, like that it goes. Anyhow, that relation should be carefully understood. If A is to be taken as an element in this A related to B, if you can find n belongs to Z such that B is equal to sigma raised to n of A. So what are the things to be given? You must be given a set A. You must choose a permutation sigma. With respect to that sigma, we can define an equivalence relation provided you have n belongs to Z satisfying this condition, B equal to sigma raised to n of A. Such A and B are related. Now we'll prove that this is an equivalence relation. Okay, as follows. Reflexivity. For n equal to 0, you see that sigma raised to 0 is equal to I. We have seen A raised to 0 equal to E in the case of any group. A raised to 0 is the identity element. Here the identity element is the identity permutation. Therefore, A is equal to I of A. That's how identity operator is or identity permutation is defined. I of A, I'll be replacing my. So what we have is A is equal to sigma raised to 0 of A. That means A is related to A. Now it's symmetric. Suppose A is related to B, then there exists by definition there exists an n belongs to Z such that B is equal to sigma raised to n of A. Now if sigma raised to n of A is equal to B, then sigma raised to minus n of B will be A. That means see inverse taken n times back means you'll be getting A. So minus n is there with A is equal to sigma raised to minus n B means this V will be related to A. So whenever A is related to B, we have B is related to A. Now transitivity, the relation can be proved to be transitive as follows. You choose A, B and C such that A is related to B and B is related to C. A is related to B means there exists n such that sigma raised to n of A is equal to B. B is related to C means there is m such that sigma raised to m of B is equal to C. As B is sigma raised to n of A, we will be getting C is equal to sigma raised to m. This is your B. So sigma raised to m of B means sigma raised to m of sigma raised to n of A. Sigma raised to m, sigma raised to n convolution means sigma raised to m plus n of A. Therefore, you can see that this relationship makes C is related to, sorry, A is related to C. A is related to C. Okay. Now, this is, so we have got a equivalence relation on A. That equivalence relation, as I told you in the beginning, will cut or will partition your A into equivalence classes. Each equivalence class with respect to this equivalence relation is what we call it as an orbit of sigma. So once again, going back to the definition, we see the definition carefully. The equivalence relation, so the equivalence classes in respect to the equivalence relation defined by A is related to B if there exists AN belongs to Z. Say that sigma raised to n of A, that's an equivalence relation we have shown. That those equivalence classes are called orbits of sigma. So there will be several orbits, more than one orbit sometimes, or simply one orbit, or more than, see, we'll have an example. So this definition should be careful. So when you hear the word orbit, you have to remember that equivalence relation and the corresponding equivalence class. So orbits are nothing but equivalence classes of that relation. So permutation is to be given. Using that permutation, you will be defining an equivalence relation, and the equivalence class partitioning this A will be cut into several equivalence classes. We'll see by an example. So, for example, if you take A as 1, 2, 3, and if you take this as a permutation, what are the orbits of the sigma? So you can see image of 1 is 3. So 1 is mapped onto 3. Now what about 3? 3 is mapped onto 1. Therefore, this 1 and 3 will be in one orbit because sigma of 1 is 3 and sigma of 3 is 1. Therefore, 1 and 3 are related. So 1 and 3 are related. They will form an equivalence relation. Now for 2, there is only one image. Therefore, image of 2 is 2, image of 2 is, so it goes, and even if you take sigma many times, all the times 2 is mapped onto 2 itself. Therefore, these are the two orbits of sigma. You see the complete A is 1, 2, 3. That A is partitioned into this equivalence class and this equivalence class. Therefore, here the orbits of sigma are the set 1, 3 and the set 2. Now, one more example to illustrate it further. Consider the example which is there in S7. That means there are 7 elements. You are dealing with A equal to 1, 2, 3, 4, 5, 6, etc. Here the permutation is mu. And what are the orbits of mu? Let us take this 1. 1 goes to 7. 1 is mapped onto 7. Now move on to 7. 7 is mapped onto 6. 7 goes to 6. Then what about 6? 6 goes to 4. 6 goes to 4. It is not over. Then what about 4? 4 goes to 3. Then 3 goes to 1. So it's over. You started with 1, ending at 1. So you can see that 1, 7, 6, 4, 3 will be in one orbit. Now what about the remaining? This is also counted. 2 goes to 2 and 5 goes to 5. They are in so the orbits are 1, 3, 4, 6, 7 in one orbit. 2 is another orbit. 5. So these are the orbits of that mu. So definition of a cycle, I told you cycle is a special kind of permutation having some property. You remember, a cycle is a permutation for which there is at most one orbit having more than one element. Look at this example. This mu is an example of a cycle because how many elements are here? 5 elements. How many elements are here? 1 element. How many elements are here? 1 element. So mu is an example of a cycle because this is an orbit containing more than one element. So in number there is only one. This is an orbit having only one element. So if count the number of orbits having more than one. So this is an orbit having more than an element. So totally there will be only one, at most one, having more than one element. We'll have one more example. For example, if you take 2 as this is in S4, what are the orbits of this? 1 goes to 3, 3 goes to 4, 4 goes to 1. Therefore 1, 3, 4 will be in one orbit, 2 is in another orbit. So how many orbits? 2 orbits, in which this is the orbit containing more than one element, and there is only one such orbit. If such is the case for a permutation, that permutation is called a cycle. One more example. Okay, we'll be writing this 2 like this. We won't be writing this expression. Instead, we'll be writing only this orbit as the cyclic rotation. We'll be having more examples in the next video. Anyhow, for the time being, we'll stop here. And okay, one more example. So this is sigma. This is not a cycle because what are the orbits? You go to 1, 2 goes to 3, 3 goes to 1. So it is an orbit. 1 goes to 3, 3 goes to 1, it's gone. 2 goes to 2 is another orbit. 2 goes to 2. Now what about 4 and 5? 4 goes to 5 and 5 goes to 4. Therefore, 4, 5 is another orbit. A last orbit is 6. 6 goes to 6. But you see, this is an orbit containing more than one element. This is an orbit containing more than one. So there are two orbits having more than one element. Therefore, sigma is not a cycle. For cycle, there must be at most one orbit having more than one element. Okay? That's we'll stop here and we'll see something more in the next